In this video, we will discuss differentials. Before we can define differentials, we're going to have to provide some motivation. So for a little bit, please just understand that differentials is a vocabulary word. We're going to leave it undefined for a couple minutes, but we will come back to it, I promise. The learning objectives that we have are to use tangent lines to linearize a function near an x value, which we will call a. We will also want to understand differentials dx and dy, most importantly with geometrically, so you understand what they are, but also how to use them algebraically. The algebraic part is important because that's what we will need to do to calculate differentials. And we can then use our calculations of differentials to calculate total and relative errors in measurement processes. You can see the vocabulary at the bottom. A lot of the vocabulary is very, very important because, well, a lot of the homework problems, a lot of the understanding for it, a lot of the ideas are based on the notion that you know what the words mean, you know how they could be applied. So the vocabulary and learning what they are is a key component because they're going to be used all over the place. Okay, now I want to stress once again, before we can start defining what differentials are, there's a process I'd like you to follow through with your calculator. And so, first things first, graph y equals x squared on your calculator. You will note I already have my graph here. But you should also determine the equation for the tangent line at the point 2, 4. Okay, so to do that, we've been doing these for a while. We know the equation of any line is y minus y1, slope x minus x1, and then the point y1 and x1 we can get from 2, 4, but we need to get the slope. And slope of the tangent line is obtained from taking the derivative, and the derivative of x squared equals 2x, but we're not looking at every single x value. We want to know the slope of the tangent line at the specific x value when it's 2, so we can plug in x equals 2 and get the slope of 4, and so here is the equation for our tangent line. I'm also going to note that you could just add 4 over and get something that we could type into our calculator, which we can then do here. Our formula was slope of 4, x minus 2 plus 4. And you'll note we could see our tangent line where we have already obtained the equation, and at the same time we've also done step 3 with graphing it on the same grid. From here we're going to come in and do our step number 4, zoom in a bunch on the point 2, 4. Well, rather than using the calculator zoom feature, I'm going to just change the window settings. Since we're centered around 2, I'm going to go 1 to the left of 2, 1 to the right of 2. The y height for the point of interest is 4, so let's go 1 below and 1 above the 4. Under this window, we could take a look at our graph and then say, what do you notice about these two? Well, it should be jumping out to you that these things are really, really close. Visually, at the top of the graph, we can see that the red and the blue lines are actually a little bit off, and at the bottom, we can see the red and the blue are a little bit off. But for the vast majority of what we're looking at in this window, our graphs look basically like they are the exact same thing. We know, of course, that they're not. If we were to zoom in really, 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 really close, we would be able to see the differences because they're only intersecting at the single tangent point 2, 4. But our observation is still valid. They're really close. And I don't mean that they are really close for the entire function, because again, if we look at the left graph, we can see that for everything left of the y-axis, they're not even close. They are way off for x values that are less than 0. That's not what we're concerned with. We are concerned with the idea that at least when we are really close to x values of 2, these things are really, really close to each other. They look very, very similar. Part of the graph almost seems like it is a line. That spot, because our tangent line is so similar to the graph, only near the point of tangency, we can approximate our function of x squared with the tangent line, at least near where the tangency is. That process is called linearization. Taking a function and approximating it with a line, the specific tangent line, is called linearization. Well, here's the big thing. We have our equation for the line, but we don't want to say this is the line everywhere. We are concerned with the specific one that had the point 2, 4, that had the slope of 4. Sorry, I underlined the wrong one. It has the point, x is 2, y is 4, and has the slope, which was f prime of 2. More generally, instead of saying 2 and 4, we will have the point A, and the height 4 came from having the function value A. This is the point we are looking at. The slope then won't be always at 2, but it was the derivative of the x value we chose. Well, when we start plugging this piece in as here's our x1, here's our y1, and the slope, we can rewrite this equation of our tangent line into something of the form y minus f of a equals f prime of a multiplied by x minus a. But because we want to be able to actually plug this thing into a calculator, we want it to be just y equals, we could add over the f of a onto the right-hand side, which essentially just lets us rewrite this as f of a plus f prime of a x minus a. This bottom equation is a function. It is the linearization of x. But it's not just the linearization of x, it's the linearization of x at x equals a. This formula is something you will need to use extensively in our work with differentials. It's going to play a significant role in how we define differentials, which again is coming up momentarily. But this process is important because it's our first learning objective. We want to use tangent lines to linearize a function near an x value called a, and this formula is exactly how we will do that. For example, if we have the function f of x equals the square root of x minus 3, and we want to linearize it near or at an a value of 7, what will we be able to do? Well, remember, the linearization of x near a equals 7 is f of a plus f prime of a multiplied by x minus a. I created this directly by using the formula we just wrote down. Well, you'll note the only things we need to do then are figure out what is f of 7? What is f prime of 7? Those are both things that are relatively quick to get. F of 7, we'll just plug in 7 minus 3. So the square root of 4 is 2. That part is 2. In order to calculate f prime of 7, we will need the derivative. So we are taking the derivative of our function, x minus 3, but the square root is a 1/2 power. So we will apply the power rule. X minus 3 to the 1/2 subtract 1 is negative 1/2. But because we've got our blob function on the inside from our function composition, the chain rule tells us we will then have to take the derivative of our interior function from the composition. Well, in this regard, we're a little bit lucky. What is the derivative of x minus 3? The derivative of x is 1. The derivative of a constant is 0. So 1 minus 0 is 1. This whole derivative is just the number 1. Well, we've got the stuff to the left times 1. Multiplying by 1 doesn't change anything. We don't need that part because the derivative was 1. But we're not going to take this derivative and plug it in just for f of x, f prime of x. Again, we want f prime not of all x's, but of the specific one of 7. When x is equal to 7, we're taking 1/2 times the negative exponent tells us 1 over. 1/2 is square root, so we have 7 minus 3. 7 minus 3 is 4, square root of 4 is 2, so we wind up with 1/2 times 1/2, which yields 1/4. Completing our linearization, a is equal to 7, and so here we go. This piece in yellow is our correct answer. It is the linearization of the square root of x minus 3 near the a value of 7. Now, because I like to have things simpler, I don't want to stop here. The yellow line absolutely is correct, but I'm going to take it further and note that we could have 2 plus 1/4 x minus 7/4, following just from the distributive property. But then the number 2, I could actually rewrite as the number 8 over 4, which is then relevant because 8 over 4 subtract 7 over 4 is 1 over 4. And instead of writing 1/4 x, I'd rather just write it as x over 4 and then say, this is my linearization, which is an equivalent form to our first line in yellow, but it's still just a little bit simpler. It's a little bit easier. I'd prefer to work with this. Okay, so we've got all this stuff. In order to clear some room, in order to make some room, I'm going to erase some of these pieces, and then I'll rewrite our linearization, because we still have not used it to say, approximate the numbers. We've obtained the linearization that we were asked to do, but now we're going to use it. Well, I guess I won't erase. I'll just scroll down. So, with what we're trying to do, we have our linearization. L of x near a of 7 is 1/4 plus x over 4. And remember, we're trying to approximate the square root of 6.98. So what we're noting then is we're trying to take advantage of the linearization of the function. The function, remember, was the root of x minus 3. When we're considering this, 6.98 is rather close to 7. Well, since if we used x as 10, 10 minus 3 would give us 7. And so we wind up with something that's similar to what we're trying to do. Well, this tells us then that if we are plugging in x for 10, you'll note that with our piece, we're using a function value of x equals 10. That tells us if we want to approximate the square root, we can actually come in and use a 10 here, which would give us 1/4 plus 10 over 4. But again, we didn't just have 10, because 10 does not give us exactly 6.98. It gave us 7. Using just a little bit smaller, instead of using x is equal to 10, if we use x is equal to 9.98, 9.98 subtract 3 does give us 6.98. So we could use the x value, 9.98. And what the linearization tells us is that this value in the yellow, because we're plugging in x is equal to 9.98, should be very close to the actual square root of 6.98. Well, let's crunch some numbers. 1/4 is 0.25, and 9 plus 98 divided by 4 equals 2.495. When we add those together, we should get 2.745. We're saying this is approximately equal to the square root of 6.98. Of course, we can grab a calculator, actually do the square root of 6.98, and see how close we really did get. So 6.98 to the 0.5 power, because of course 0.5 is a half, half is a square root. We get the better approximation that the calculator used of 2.64197, which we could see how close it is. 64197 would be 642. Was our approximation good? Well, not too bad. At least we're within 1/100th of each other. Or, I'm sorry, not 1/100th, 1/10 of each other. So it's not horrible. It's not like we were getting something that was 30. But being off by a whole 0.1 is still not that perfect. Why aren't we getting a better answer? The answer still lies in our linearization. We used this value, and we said this is true near values of a equals 7. That's telling us when we go down here to actually use it, the closer a number is to 7, the better off our approximation will actually be. If we were trying to take something like the square root of 312, because 312 is so far away from 7, using this linearization would give us wildly inaccurate, very, very far off. The closer we can get to 7, the better we'll be. This is just illustrating that we actually can use a linearization for other values, but you want to pick things that are really, really close. We could do this exact same thing for the square root of 7.05 and just repeat this piece with 7.05 is equal to 10.05 minus 3. So when we take our square root, we could plug in, instead of 7, or instead of 9.98, we could plug in 10.05 and just replace these numbers, 1/4 plus 10.05 over 4, and that value equals 2.7625. And if we go use our calculator, 10.05 to the 1/2 power is actually 3.17. You can see we were right on that edge where we're starting to get farther off. We're at this point where if we are going farther and farther past 10, our approximations are going to get farther and farther away. It is a lot better if we were trying to do the square root, approximate something near the square root of 10. It would have been better to do the linearization not near 7, but do the linearization near 10. Pick numbers that are near what we're trying to approximate. Okay, now we will continue this part. Let's say we want to know, if I want accuracy that's going to be within 0.5, how close do we actually need to get? So, for example, here, we were looking at it and saying, looking at this particular component, how far off was I in the first one? Our first approximation was far apart by about 0.1. This would be an error. For the second one, 3.17 minus 2.76 is off by approximately 0.41. This is the amount of error. If we would like it to be, or rather, if we want to know which x numbers can we use that will stay within this error tolerance of being within 0.5, which x values can we actually use? Well, the big clue there is we're talking about being within a distance. Within the distance says we can be above it, we can be below it, but distance is absolute value. So one way that we could look at this is saying our function f of x, we could subtract off our linearization and say the distance between these two has to be less than 0.5. Well, remembering back from your early days of algebra, you should note that if you want to solve if you want to solve an absolute value inequality of this form, one equivalent way to write it is negative 0.5 is less than our stuff in the middle, which is less than positive 0.5. And there are other ways that we can write it. Our textbook actually provides a different one. But the key feature that we're noting then is we just want to know, when is this compound inequality true? Now in class, I was going to show the students how we could do this algebraically. The algebra got a little bit complex, and so people made the decision, let's use the calculator as a strategy instead. The textbook actually used the same strategy. They just used a different form of inequality with their example. Ultimately, though, here's what we've got to note. This will be our f of x in the calculator. Type that in and graph it. You'll note I paused the video, typed it into my calculator, and here's what I obtained. We are interested, again, in when is this piece in between the height of negative 0.5 and positive 0.5. I'm seeing something I did wrong. I typed in the function incorrectly. You notice how my equation is saying plus x over 4? It's supposed to be a minus x over 4. I typed it in the calculator wrong, which is why we're seeing some pieces not working. We'll have to come back, edit that function, and fix it. And when we fixed it, this is what we wind up getting. And I'm trying to move some of the, whoa, did not want to do that. Okay, in order to fix the weirdness that happened with the calculator, I'm not quite sure what I did to cause it to go freak out on me. But I fixed that. You'll notice behind the table, the window settings, they're horizontal again. While I was at it, I decided to change the window so that we can zoom in on only the stuff we want, because we didn't care about all the stuff that was happening on the left. Changing my window settings so that we're going from -1 to +1 which still encompasses our negative 0.5 to positive 0.5, we wind up with this graph. You're still noting there's a lot of stuff that appears to be going on the right-hand side of the graph that we can't see. Like we don't know if this graph in the blue is going to keep going down or if it turns around and starts going up. So we're going to come back in, change the window settings again to widen it. Instead of going to 10, let's take a guess. I'm going to try 20. I don't know if my guess is going to be enough, but we can take a quick guess and try it. And we can see, okay, it's starting to go outside our range. This is the key feature that we're noting. We want to know when is our graph in between the two heights of negative 0.5 and positive 0.5. Graphically, we can see it's in this blue region above the blue line. And so what we can use is the calculator's intersect feature to simply get those x values. And in order to help speed up that process, I'm going to get rid of graph 3 because it never goes above that line. And so what we'll wind up saying then is menu, analyze graph, intersection, left and right hand side, and we get the intersection at 3.34, approximately. And we can do the exact same thing, intersection on the left hand side and the right hand side, and get about 14.7. Well, those x values are the solutions for what we had. This inequality is true when we're going from 3.34 up to 14.7. Approximately. We know the answers have been rounded, but this gives us some ideas. If we want our square root approximation to be within an error tolerance of 0.5, this is how close we need to be. Well, what if we want to be within an error tolerance of 0.1? What if being off by 0.5 is too big of a mistake? Well, the only thing that changes then is we've got to be within 0.1, which tells us negative 0.1 and positive 0.1. And that's only going to change the values on our graph. Tab, nope. So tab, we can do the height of 0.1, and I'll go tab, we'll go into my history, and go into this one and change it to negative 0.1, and we can now see the same issue. I still don't need the blue line, but you can also tell the window for the x values that will still work has shrunk. I can go right back into using the intersect feature. Left-hand side, right-hand side, menu, intersect, left-hand side, right-hand side, and we are getting the two values from 4.87 up to 9.93. If we want to stay within an error tolerance of 0.1, we would need to stay, I forgot what the numbers are, 4.87 up to 9.93. Anything within these values will still be within 0.1 of the actual function value. So, we still have not said anything about differentials whatsoever. We did all this stuff with linearization, and you were like, oh, sweet, yeah, cool. We've got the linearization function. We went through and looked at how do you linearize the function, which was our first, our first learning objective. But we still haven't done any of our other learning objectives. The next one is understanding differentials, and we needed to do the linearization so that we could understand what differentials are. Differentials, in terms of the algebraic notation, are these pieces. dx and dy are differentials. Geometrically, they have a very simple, straightforward interpretation. If we are looking at an x value near A, we could draw a tangent line, okay? And I intentionally drew this tangent line not supremely perfect because what we're going to concern ourselves with is we could pick an x value, x1 to x2. You will note if we come straight up, it intersects our original function f of x, and it also is intersecting our linearization L of x. Please note this isn't just, okay, let me finish off the rest of this. It's intersecting both the function and the linearization. Within those, we could look at it and say, for our function, we could have rise and run, and I actually said it backwards, but we could say where those 2 points are crossing, we have rise and run. The run is actually delta x. This piece is the run in the actual function f. When we're changing from x1 over to x2, delta x is the actual run. Delta y is the rise in the function f when we're looking at these 2 points. Basically, it's the idea is if we're doing a secant line, these are the pieces that make up the slope of our secant line. But when we do the tangent line, this is what we are running into. Well, it's still not perfectly tangent, but in our linearization, we still have 2 points where they're intersecting our vertical lines, x1 and x2, and they are coming over, and they are still forming another right triangle where we have rise and run. dx is the run in the linearization. Not at the original function, but in the linearization of the function, dx is it. You'll probably notice that's the exact same thing. There is absolutely no difference. dx is actually the exact same thing as delta x because the run between them is x2 minus x1. It doesn't matter which function we're looking at. The original function in blue or its linearization in black, they are actually the same piece. And when we are looking at these pieces, it looks like we are going to have dy actually equal to delta y as well. But we don't know that. We're looking at this piece and saying, this is the height in purple for delta y. And this is our height dy. Well, are they actually the same? No. The size of this little extra gap that we're getting here does not match up with how much we're losing down at the bottom. Maybe it's kind of close, but they're not exactly the same. It is incorrect to say dy is equal to delta y. Instead, we are going to wind up with using our linearization to approximate. These pieces are not equal to each other, but they are approximately equal to each other. We would like to have a way of getting them to be a little bit more precise. Specifically, we want to create an equation that will allow us to say dy is equal to something. How can we get dy? I'm going to scroll down here so that we can develop some of the algebra that will allow us to calculate how to get this dy. Here's our major feature. We could start off by saying y, I wanted this in black, y is equal to f of x. if we take the derivative of both sides, on the left, we get dy dx, and on the right, we get f prime of x. Well, our notation for dy dx wasn't an accident. The derivative, remember, is slope. Dy is rise. Dx is run. So rise over run is equal to the derivative. All we're really doing is saying, I'm going to take the dx and multiply it because dx is not 0. And then we're saying exactly what we need to. Dy we can calculate by taking f prime of x and multiply it by dx. The rise is equal to the derivative multiplied by the run. That's what we wind up getting here. This is a formula that when you are working with differentials is very beneficial. It's not difficult to memorize dy is equal to dx, but dy is equal to dx, I'm sorry. Dx is equal to delta x. I misspoke originally. But dy is equal to f prime of x times dx. This is a piece that we are going to use. Again, in terms of our learning objectives, we want to understand differentials dx and dy geometrically. That learning objective applies to this piece right here. Dx and dy, dx is the run in Ella in our linearization, dy is the rise in the linearization. If you want to get the actual values of dy and dx, the algebraic understanding, that is these two equations. Dx is equal to delta x, and dy can be calculated here. Those are another one of our learning objectives. Okay, so now how are we going to use our differentials? One thing that we would like to do is to compare the values of delta y and dy if f of x is equal to this function x cubed minus 2x plus 1. But we're doing them from an x1 value over to the x2 value. So here's where we're going to start. We know delta y is actually equal to the change in height between the actual function values. Using this, we can calculate the actual change, delta y, in the y height of our function. We will come back and crunch those numbers in a second. Dy is equal to, reminding you back on the last page, f prime of x times dx. So we're looking f prime of, this is f prime of our major feature we're looking at. This is going to be for the x value of 2. We're actually going to come back to that one, and I'm going to leave this as f prime of x, and then we'll look at this specifically in a second. But for right now, what we're noting, here's our formula. Let's crunch some numbers now. I'm going to come up, and let's crunch delta y first. Okay, so f of x2. We can come over to our calculator and insert calculator page, and I'm just going to type in our function x to the third power minus 2x plus 1, minus 2x plus 1. Oh, dang it, I put them all in the exponent. Minus 2x plus 1. And I'm going to use our given that x is equal to, and we wanted it from 2 to 2.05. So 2.05. And the same thing, given that x is equal to 2, there we go. So if we're taking x2, f of x2, subtract f of x1, that is 5.51 subtract 5. In terms of its approximation, rounding it to 2 significant digits. Oh, wrong one. There we go. 5.52 minus 5 is 0.52. This is the actual change, rounded to 2 significant digits, of our change in the height. Next, we will come and do dy. F prime of x, we'll take our derivative, that's 3x squared minus 2, multiplied by dx. Well, here's the big thing about these particular ones. We're using our dx from 2 to 2.05. dx is then just 0.05. I don't know why I put 2 points in there. I think this was intended to be a multiplication in my brain. But then the derivative needs to have a specific x value. Well, it makes sense to use the 2. That's where I was mentioning before. So we would have 3 times 2 squared minus 2, which would give us 12 subtract 2 is 10. 10 times 0.05 is 0.5. And you'll note 0.50 is pretty dang close to 0.52. Delta y and dy are not exactly equal, but they're ballpark close. They're approximately equal. So compare the values. We just did that. Here's our comparison. Delta y is 0.52 and dy is 0.5. So delta y is just a little bit bigger than dy in this particular problem. We're asked to do the exact same thing if we're going from 2 to 2.01. Well, for the most part, a lot of this stuff is going to stay the same. We still have the same derivative, but I'm going to switch this to this orange color. Our dx is no longer 0.05, it's 0.01. So 10 times 0.01 winds up giving us 0.10. And we'll have to go back and get our new f of x2. We still have f of x1, but f of x2 is going to change. And we can go right back to the calculator and get that one pretty quick. So we'll go 2.01. So 5.1006 subtract 5 is, where was I? 5.1006. That winds up being 0.1006. And so when we compare 0.10 and 0.1006, they're really, really close. Indicating that the smaller we make delta x, or the smaller that we make dx, the better this approximation becomes. If we shrink down the size of this, if we make this, I'll switch this one to a different color. I'll use this, I don't know, let's use this teal, because teal is ugly. If we shrink down the size of dx, the actual difference between delta y and dy is going to become smaller and smaller. I know that does not seem like a big deal to you right now, but this is a piece that is going to play a role for us down the line in the class. Specifically, in our 4th unit, when we are working with a topic called integrals, this plays a role, and it will actually be helpful. It plays a role in helping us define something that is important further down the line of the class. This is in large part a setup for something that is absolutely enormously critical down the line. Trying to understand the difference between delta y and delta x will be important. It does play a role. Please don't just completely blow this off. But just because it's really, really, really important later doesn't mean it's completely useless now. We could use differentials to create a problem that's similar to this, or rather to answer questions like this. The radius of a sphere was measured and was found to be 15 centimeters, but there was a possible error in measurement, but at least the equipment was good enough so that the error is at most 0.05 centimeters. What is the maximum error in using this value of the radius to complete the volume of the sphere? Specifically, here's the stuff that we're looking at. We know if this is the biggest possible error that we could be allowed, that tells us the radius in reality could be 15 minus this error. 15 minus 0.05 is 14.95. Or it could possibly have gone up to 0.05 above, and so we have 15.05. We know the actual radius is somewhere in this interval. So if we start using the volume formula, volume of a sphere is 4/3 pi r cubed. Well, if we're starting to estimate the volume of the cube with stuff that's wrong, if we are plugging in 15 for the formula when it's in actuality 14.96 or 15.02, this estimate that we get for the volume is, but how far wrong? How big of a mistake could it be? Are we talking about a mistake that's only 0.1 centimeters big, 1.1 cubic centimeters big? Are we talking about something that's 50 cubic centimeters error? Are we talking about 1,000,000 cubic centimeters error? Incorrectly measuring the radius, or making a mistake because of our tools just might have a potential mistake built into them. If there is some small mistake in measuring the radius, it will cause an error in the actual measurement or the actual calculation of the volume. How big is that mistake? In terms of our vocabulary that we had before, that would be related to our relative error. Was it a big mistake or was it a small mistake? We'll actually come back to that in a moment. But how much is it actually off? This is where differentials could be used. Answering that question plays a role, because we could take the volume formula. Well, I've already got it written there, so I'll just continue it here. And if we take the derivative of both pieces with respect to r, we'd get dv dr equals 4 pi r squared. If we just multiply by our dr, these pieces cancel, and we then get, and I'm just going to erase it instead of writing a whole new line, dv is equal to this. And I want to write that a little bit lower just so it looks better. I'm kind of weird that way, and I want it to look straight in a line. Well, this tells us that we can estimate the amount of error. Oh, we can go with this one. We can estimate the amount of error in the volume by using this formula, which takes advantage where we already know the potential error in the radius. Well, we'll just start crunching some numbers then. 4 times pi times the radius. Our radius is 15. And then multiply by dr. Dr, the error in measuring the radius, we already knew. Dr is the same as dx. I'm sorry, dr is the same as delta r, the change, the possible error. So we'll multiply that by 0.05, and we can just directly use this in our calculator now. 4 times pi times 225 times 0.05 equals 141.372. This tells us we could be off by as much as 141.372 cubic centimeters. When we are measuring it, well, of course, 1 cubic centimeter is a milliliter. So in terms of volume, we could be off by 141.372 milliliters in the calculation of our volume. Is 141 centimeters off, or is 141 milliliters off a lot? Well, you're off by 141. 141 seems like it's this really, really big deal. But if we're off 140 milliliters for the volume of the entire planet, that doesn't seem like such a big deal. If we're off by 140 milliliters on the volume of a marble or a pea, yeah, that's a huge error. This is where relative error comes into play. Relative error is like our percentage error. If we take the actual total error, 141.372, and divide it by the total volume, we would be able to get a percentage error. Well, the last thing we need to do is actually go through and calculate the volume. We haven't done that yet, so quickly crunching the numbers for our volume here. Remember, volume is 4/3 pi times radius cubed. If we just crunch those numbers, we will obtain a volume of 14,137.2. So if we're taking our volume then, 14,137.2, and dividing that out, we would get 0.01, which is just 1%. So is it really that big of a deal? In the grand scheme of things, when we're looking at this, if our measurement tool allows us to be off by as much as 0.05 for a radius of 15 centimeters, it would tell us that the maximum error is possibly up to a 1% error. And so when you're like, hey, that's 99%, you're like, oh, yeah, so what? That's not a big deal. But of course, if we use something that's 150 centimeters, the error percentage would be smaller. But if we only had 1.5 centimeters, that error would be bigger. It depends on, or the relative error, the percentage error would be bigger. That's what we're looking at. So, to sum up, please note our learning objectives. Tangent lines can linearize a function near A. Tangent lines can approximate functions as long as you're taking your tangent line near where your derivative is, near a specific x value called A. You should understand differentials dx and dy as the rise and run of the linearization. That's geometric. But you should also know the formulas for how you would be able to calculate dx and how you could calculate dy. Those formulas we would use to calculate differentials. And then we saw, with our last problem, that you could use differentials to calculate the total amount of error and the relative or percentage error in a problem. Those things combined tell us all the pieces that we would need to know for now about differentials.